So this is the little video I was going to make regarding electron structure. I decided it might be good to review just a light math discussion that we did in class the other day. So we said that light has a dual nature. We talked briefly about that. We know that light travels in waves like this. The distance from here to here is called the wavelength, which we would represent by the symbol lambda. So that's wavelength. And the number of times it goes up and down per unit of time is called the frequency, which we represent as nu. So we have these two variables, lambda and nu. They're a little out of focus. There you go. Sometimes chemistry concepts are a little hazy. So we have the wavelength and we had the frequency. And then we had two equations involving these two variables. Both equations had a constant. So it might be helpful, this is not technically correct, but sometimes helpful to think about this wave is actually made of a bunch of little particles traveling in waves. So you could think about the energy of each one of those particles being written like this, that the energy is proportional to the frequency. And we saw in the spring demonstration in class, for those of you who are not in my class, I usually don't like to do that in the fall, but we decided to go ahead and do it this year in the fall, because you know it's a spring demonstration. But anyway, we use the spring to illustrate the wavelengths, and we know that the energy is proportional to the frequency. And when the wave was going real fast, it was a high energy wave. So the proportionality constant is h. H is Planck's constant, and h has this numerical value. H is just basically the same kind of thing as pi. You know, like the area of a circle is pi r squared and so on. H is just a different constant, a different number, but it serves the same purpose. It's a proportionality constant. So the numerical value for h was that times 6.63 times 10 to the negative 34th joules per hertz. Now, of course, since a joule per hertz really means a joule per 1 over seconds, sometimes you'll see the Planck's constant written as 6.63 times 10 to the negative 34th joule seconds. So that makes sense if you see it. We didn't talk about that in class yesterday, but it's viable to use joule seconds instead of joules per hertz. All right, so that's the first equation, and this treats light as a particle. Now we also know that light has this wave nature, and so the other equation that we learned about was that the speed of that wave is equal to the wavelength multiplied by the frequency. This, by the way, is the same variable. I kind of got carried away with my tail there. All right, the numerical value of c is, we're just going to use 3.00 times 10 to the 8th, which is a little bit high, but we'll just use that. So that's simple to work with. Meters per second. All right, so those are the two equations. The one on the left deals with light as a particle, and the one on the right deals with light as a wave. And so when I'm talking about light as a particle, this is what I'm talking about. So we're going to share a screen here and see if I can pull up the little animation we had yesterday in class. So there's my little animation. You see my little electron floating around right here. And this electron right now is excited because he's away from his ground state. But in just a minute he's going to go to the ground state. Oh, and see that little particle of light that came off. So these particles that are floating through our screen here, those are particles of light. The electron is here, the proton's in the nucleus. This is a hydrogen atom, so there's only one proton and one electron. We don't have any neutrons. All right, so this electron is excited, and when he comes back down, he gives off energy. So the equation E equals h nu, that is this equation, represents the energy of the little photon that we see being emitted. And of course, if the electron falls from here to there, it's a different energy photon than it is if it falls from there to there. So it's the energy of the photon going in this direction that we're talking about when we talk about the E equals h nu. So here comes another. He's excited. He's going to come back down. Sometime, there he goes. And see this little thing right here? And notice that electron's on a second energy level right now. And notice this is a colored photon. When the electrons fall to the second energy level, they emit light that we can see. When they fall to the first, they emit this little thing as ultraviolet light, and we can't see that. All right, we can actually calculate the energies of each one of these rings, but we're going to leave that for another day. But it is in Chapter 7 of your text, if you'd like to explore that. Took a second to look up the page number. I say Chapter 7, it's in Chapter 8, but I'm not going to take time to look up the page because it's going to take me a minute and I don't want to make the video long. All right, so anyway, there's an equation to calculate the energy here, but the energy in the E equals h nu equation is not the energy of each ring, it's the energy that the photon has when he leaves. Then while we're on this picture, I want to just show you also, we mentioned briefly the Schrodinger equation yesterday. So if you think of it as Schrodinger thought about it, you wouldn't see rings, you wouldn't see the electron. But when the electron absorbs light, what happens is we would create a waveform of a particular shape. There you go. See, that is the electron. It'd just be a fuzzy region where you'd find the electron. And when the electron loses energy, that little waveform is going to go away and it's going to emit light. Okay, so we know that one probably fell to the first energy level because that's ultraviolet light. And if we let it sit here for a little while, we'll get another waveform as the electron gets excited and moves further from the nucleus. There's another one. All right, so you see they look different depending on how much energy the electron gains from these little light particles, and then when they come back down, they give off light. All right, so that's the Schrodinger perspective, a little more concrete using the Bohr perspective. All right, then, so those are the two equations. I'll let you do the math that's on the homework assignment I gave you. I also we ended by briefly in class yesterday talking about the wavelength of matter. So since light has a dual nature, that matter could have a dual nature also maybe. So light acts like matter, maybe matter acts like light. And that's important because if you look at an electron, you change it because they're so low in mass. When light hits the electron, it actually changes its position. So that was the Heisenberg uncertainty principle that I mentioned, that you really can't see an electron and tell where it's going at the same time, so then you can't really look at it, and it doesn't make sense to treat it as a particle. So we have to think, well, maybe matter could have a wavelength, and we developed this equation that wavelength is equal to mass times velocity. So the mass, and that's equal, oh, I didn't write that down correctly, did I? Wavelength is equal to h divided by mass times velocity. My mind moved ahead before I finished my previous thought. So what that means is this is a constant. And what that means is that the wavelength is equal to a constant divided by mass times velocity. So since that's constant, as this number gets bigger down here, the mass times the velocity gets bigger. It's also called momentum if you're into this sort of thing. So as the momentum gets bigger, which means as the mass gets bigger, then the wavelength gets smaller. Okay, so for us, as we walk down the hallway, we don't notice it. We don't notice a change in direction when they turn on the lights because we're very massive. But electrons are not very massive. So if I zip out here and check out the mass of an electron, let's just see what we find. So we'll go to a new tab here on my little computer screen, and we'll do mass of electron. And it's 9.1 times 10 to the negative 31st kilograms. All right, then if we look at the velocity of an electron in an atom, I don't know if that's going to pop up so easily or not. Let's see what I can find right here. I'm going to stop the video just a second, and I'll get a valid number for that. So I'll stop recording and we'll come back to part 2.